Welcome everybody once again. So we are in our third module and this is our 10th class. In the last class we saw some problems on orifices. That is small orifices. We saw problems on small orifices because the head of the orifice was greater than 5 times the depth of the orifice. So those orifices were small orifices. Now we are moving to next problems. That is our next problem is find the discharge through a rectangular orifice 2-meter wide and 1.5-meter deep fitted into a water tank. So we have a water tank. We will draw a water tank. We have a water tank. Okay, we have a water tank and there is a rectangular orifice. So this water tank consists of a rectangular orifice of 2 meter. Okay. So this rectangular orifice is 2 meter wide and 1.5 meter deep. So this orifice is 1.5 meter deep and 2 meter wide. Okay, this is 2 meter by 1.5 meter. Fitted to a water tank. The water level in the tank is 3 meter above the top edge of the orifice. So above the top edge of the orifice, the level of water is 3 meter. So from the top edge of the orifice, the level of water is 3 meter. The water level in the tank is 3 meter above the top edge of the orifice. Take CD is equal to 0.62. Now we need to find what is our discharge. So how will we solve this problem? See, breadth of the orifice is given as 2 meter and the depth of the orifice is given as 1.5 meter. So the height above the top of the orifice is given as 3 meter. So we will take H1 is equal to 3 meter. That is height above the top of the orifice. That means height above the bottom edge of the orifice. Up to the bottom edge, it is 4.5 meter. So from the top edge, it is taken as H1 is equal to 3 meter. From the bottom edge of the orifice, so H2 is taken as 4.5 meter. This 3 plus 1.5, it is 4.5 meter. And it is also given CD is equal to 0.62. That is coefficient of discharge is 0.62. Now, see what is the condition for large orifices? The condition is the head of the orifice. The head of the liquid to the head of orifice or the depth of orifice. So if it is large orifices, this should be less than 5. Okay, that is head of the liquid. So here the head of the liquid is, this is 1.5. So the head is taken from the center line of the orifice. So it is 0.75. So 3 plus 0.75. 3 plus 0.75 is the head of the liquid and depth of the orifice is 1.5 meter. So this is less than 5, which implies our orifice is large orifice. Okay, now if the orifice is large orifice, the formula for determining the discharge is Q is equal to CD into B into root of 2G into, so the formula is 2 by 3 CD into B into root of 2G into H2 raised to 3 by 2 minus H1 raised to 3 by 2. So we have studied this formula in the previous classes when we studied about the theory of large orifices. What is the discharge? So it is formula is 2 by 3 CD B, that is breadth of the orifice, multiplied by square root of 2G into H2 raised to 3 by 2 minus H1 raised to 3 by 2. Where H2 is the head of the water, head of the liquid from the bottom of the orifice. H1 is the head of the liquid from the top of the orifice. So substituting, we get Q is equal to 2 by 3 into CD is given as 0.62 multiplied by breadth is given as 2 into square root of 2 into 9.81 multiplied by H2 is 4.5 meter. So 4.5 raised to 3 by 2 minus H1 is 3 meter. So 3 raised to 3 by 2. So we get Q is equal to 15.917 meter cube per second. So this is our answer. Next problem. A rectangular orifice 0.9 meter wide and 1.2 meter deep is discharging water from a vessel. So we have a vessel. So this vessel consists of a rectangular orifice. So there is a rectangular orifice. So this rectangular orifice is 0.9 meter wide and 1.2 meter deep. That means breadth of orifice, right? So breadth of orifice B is equal to 0.9 meter and the depth of orifice small d is equal to 1.2 meter. It is discharging the water from a vessel. The top edge of the orifice is 0.6 meter below the water surface in the vessel. So we have water here. So top edge of the orifice is 0.6 meter below the free water surface. That means our H1 is equal to 0.6 meter. Calculate the discharge through the orifice if CD is equal to. So CD is given as 0.6. Now what is H2? H2 is equal to this 0.6 plus the depth is 1.2 meter. So it is 1.2 plus 0.6, we get 1.8 meter. So H2 is from the bottom of the orifice. The distance from the depth from the free surface of water to the depth of the orifice. So 0.6 plus 1.2, we get 1.8 meter. Now you see what is the depth of, that is head of liquid in the vessel divided by depth of orifice. So head of liquid is 0.6 plus 1.8 divided by 2, that is 0.9 divided by depth of the orifice is 1.2. So this will be less than 5, which implies this is a large orifice. Okay, so now we will determine our discharge. So we know the formula of discharge Q is equal to 2 by 3 into CD into B into root of 2G multiplied by H2 raised to 3 by 2 minus H1 raised to 3 by 2. So substituting, we get 2 by 3 into CD is given as 0.6 multiplied by B is 0.9 multiplied by square root of 2 into 9.81 into H2 is 1.8 raised to 3 by 2 minus H1 is 0.6 raised to 3 by 2. So we get our discharge Q is equal to 3.1097 meter cube per second. Now, and find the percentage error if the orifice is treated as a small orifice. See, if the orifice is treated as a small orifice, we know the discharge for the smaller orifice is CD into area of the orifice into root of 2GH. So we get, see, area of the CD is given as 0.6 into area of the orifice. This is a rectangular orifice. So area of the orifice is 0.9 into 1.2. So 0.9 multiplied by 1.2 into square root of 2 into 9.81 into H. Head of the orifice will be taken this from the center of the orifice. So 0.6 plus 1.2 divided by 2. So H is equal to 0.6 plus 1.2 divided by 2. That is 0.6 plus 0.6. So here also, see, head of the liquid is 0.6 plus 1.2 divided by 2. Head of the orifice, this divided by 2. So 0.6 plus 0.6, it is 1.2. So H is 1.2. 1.2 meter. So we get the discharge through the smaller orifice. If you are considering the orifice as a small orifice, the discharge will be equal to 3.1442 meter cube per second. So there is some difference in the discharge when we are considering it as a large orifice and when we are considering it as a small orifice. So the percentage error will be equal to Q1 minus Q divided by Q, because originally it is Q, right? Originally it is in reality it is a large orifice. But when we are considering the orifice as a small orifice, the discharge is larger. So Q1 minus Q2 by Q, we get 3.1442 minus 3.1097 divided by 3.1442. We get the percentage as 0.01109, or in terms of percentage it is 1.109 percentage. This is the percentage error. Percentage error when you are considering the orifice as a small orifice. So the next problem is find the discharge through a fully submerged orifice. Next is submerged orifice, fully submerged orifice. Okay. So find the discharge through a fully submerged orifice of width 2 meter. So the submerged orifice, the width of the orifice is 2 meter. If the difference of water level on the both the sides of the orifice. So because it is a submerged orifice, okay, so water is traveling like this. The orifice is, the width of the orifice is 2 meter. So B is equal to 2 meter. If the difference of water level on both the sides of the orifice is 50 centimeter. So how can we find the difference in water level? It is taken as capital H. So capital H is equal to 50 centimeter, that is 0.5 meter. So here the water level may be like this, and here in the collecting tank, this may be the water surface. So this is H. So this difference is 0.5 meter. The difference in water level on both the sides of the orifice. Okay, so H is 0.5 meter. The height of water from the top and bottom of the orifices are 2.5 meter and 2.75 meter respectively. That is, our H1 is equal to 2.5 meter. This is 2.5 meter. H1 is 2.5 meter and H2 is 2.75 meter. Okay, so H1 is 2.5 meter, H2 is 2.75 meter. That means the depth of the orifice will be equal to H2 minus H1. So the depth of the orifice is 0.25 meter. 0.25 meter is the depth of the orifice. So we know the discharge, the formula for discharge for a fully submerged orifices Q is equal to CD into B into root of 2GH multiplied by H2 minus H1. So substituting the values, we get CD is equal to, CD is given in the problem as 0.6. So 0.6 into 2 into square root of 2 into 9.81 multiplied by 0.5 into H2 is 2.75 minus H1 is 2.5. So we get the discharge Q is equal to 0.9396 meter cube per second. We will move on to our next problem. So the next problem is find the discharge through a totally drowned orifice. Okay, so totally drowned orifice, nothing but fully submerged orifice. So find the discharge through a totally drowned orifice which is 2 meter wide and 1 meter deep. So totally drowned orifice. So the orifice is 2 meter wide, 2 meter by 1 meter deep. So breadth of the orifice is 2 meter and the depth of the orifice is 1 meter. If the difference of water level on both the sides of the orifice be 3 meter. So the difference in water level on both the sides is given as 3 meter. That is, H is given as 3 meter. Also, coefficient of discharge is given as 0.62. We know the formula as for the fully submerged orifices CD into area of the orifice multiplied by square root of 2GH. Here because other details are not given in the problem. So you can take it as area of the orifice into square root of 2GH. So we get CD is 0.62 into area of the orifice is 2 meter by 1 meter multiplied by square root of 2 into 9.81 multiplied by H is 3 meter. So we get 9.513 meter cube per second. Because the details of H1 and H2 is not given in the problem. So you can take it as the depth of the orifice. See, in the previous problem, the formula is both fully submerged or drowned. It means the same. It is H2 minus H1. If it is H2 minus H1, H2 minus H1 is the depth of orifice. That is nothing but, if you are considering the formula, Q is equal to CD into B into D. That is area of the orifice multiplied by square root of 2GH. Okay. So now I think it is clear for you. We will move on to the next problem, problem number 12. So the next problem is a rectangular orifice 2 meter width and 1.2 meter deep is fitted in one side of a large tank. So we have a tank, and in this tank on one side of the tank there is an orifice. So the width of the orifice is 2 meter and the depth of the orifice is 1.2 meter. So breadth of the orifice is 2 meter, depth of the orifice is 1.2 meter. The water level on one side of the orifice is 3 meter above the top edge of the orifice, while on the other side of the orifice the water level is 0.5 meter. So one side from the water level on one side of the orifice is 3 meter above the top edge of the orifice. So it is 3 meter, and on the other side from the top edge of the orifice the water level is 0.5 meter. So it is 0.5 meter. Calculate the discharge through the orifice if CD is given as 0.64. Okay. So how will we solve this problem? So B is 2 meter, depth of the orifice is 1.2 meter. Now height of the water from the top edge of the orifice, it is given as 3 meter. So we can take H1 is equal to 3 meter. And it is given on the other side of the orifice the water level is 0.5 meter below its top edge. So this is not correct. It is 0.5 meter below the top edge. So it is 1.2 meter deep. So the water level is somewhere here. So this distance is 0.5 meter. From the top edge, the water level is 0.5 meter. That means what is the difference in water level between on both sides of the orifice? So the difference in water level on both sides of the orifices will be equal to, this is 3, it is this distance is down of, see, below this upper edge of the orifice, below upper edge of the orifice. So total difference in water level on the two sides of the orifice is 3 plus 0.5, it is 3.5 meter. So what is H2? So H2 will be equal to this H1 plus depth of the orifice. So H2 will be equal to 3 plus 1.2, that is height of the water from the bottom edge of the orifice, that is H2. Height of the water from the bottom edge of the orifice is H2. So H2 will be equal to 3 plus 1.2, that is 4.2 meter. 4.2 meter. Now, see here on both sides of the orifice you can check. Here the water level is above the top of the orifice. On the right side the water level is below the top edge of the orifice, which means it is a partially submerged orifice. So if it is a partially submerged orifice, we know the formula for the discharge of the orifice Q will be equal to Q1 plus Q2. That is discharge for fully submerged orifice plus discharge for partially submerged orifice. So Q1 will be equal to CD into B into D, that is depth of the orifice, H2 minus H1, right? That is the depth of the orifice. into square root of 2gh. 2gh. So this difference in water level on both the side of the orifice, that is h, plus Q2 will be equal to partially submerged orifices. So 2 by 3 CD into B into root of 2G into H raised to 3 by 2 minus H1 raised to 3 by 2. So what we get is, we can substitute CD is 0.64, B is 2, D is 1.2 into square root of 2 into 9.81 into H is 3.5 plus 2 by 3 into 0.64 multiplied by B is 2 into square root of 2 into 9.81. H is 3.5 raised to 3 by 2 minus H1 is 3 raised to 3 by 2. So we get the discharge Q is equal to 12.5329 meter cube per second. Now we will move on to our next problem. Next problem is a circular water tank. So water tank is circular of diameter 4 meter, contains water up to a height of 5 meter. That means the diameter of the circular water tank D is 4 meter. It contains water up to a height of 5 meter. That means our initial height H1 is equal to 5 meter. The tank is provided with an orifice of diameter 0.5 meter. Diameter of the orifice is 0.5 meter. That means area of the orifice will be equal to pi d square by 4, pi into 0.5 square divided by 4. So area of the orifice is 0.1963 meter square. Now see, from this the diameter of the tank is 4 meter. So area of the tank, capital A, will be equal to, so this we can take it as a small a. Area of the orifice is a small a. The area of the tank is capital A, pi d square by 4. So pi into 4 square divided by 4, we get 12.566 meter square. Now find the time taken by water to fall from 5 meter to 2 meter. So H1 is 5 meter and H2 is 2 meter. Also CD is given as 0.6. So first case, the water is falling from 5 meter to 2 meter. So we know the time required is equal to, so H1 is 5 meter, H2 is 2 meter. Okay. So time is equal to, time required to empty the tank from height H1 to H2 will be equal to 2A divided by CD into small a, that is area of the orifice, into root of 2G into root of H1 minus root of H2. So we get 2 into area of the tank is 12.566 divided by CD is given as 0.6. Area of the orifice is 0.1963 into square root of 2 into 9.81 into root of H1 is 5 minus root of H2 is root 2. So we get the time required to empty the tank from 5 meter to 2 meter is 39.58 seconds. Now second case, for completely emptying the tank. For completely emptying the tank means, first the height is 5 meter. then the height is 2 meter. So completely emptying the tank means H2 becomes 0. So H1 becomes 5 meter and H2 becomes 0 for completely emptying the tank. So the time required is 2a by CD into small a into root of 2g into root of H1. So substituting the values, we get the time required to completely emptying the tank is 107.7 seconds. We will move on to the next problem. Two more problems. So the next problem is a hemispherical tank. Just the differences in formula, right? The hemispherical tank of diameter 4 meter. I have given you the formulas earlier. Just to substitute the formula and take the answer. That's all. A hemispherical tank of diameter 4 meter. So diameter of the hemispherical tank is 4 meter. It contains water up to a height of 1.5 meter. So H1 is equal to 1.5 meter. An orifice of diameter 5 meter is provided at the bottom of the tank. Sorry, an orifice of diameter 5 centimeter. This is not meter, 5 centimeter. 5 centimeter. So it is equal to 0.05 meter. From which we get area of the orifice is equal to pi d square by 4. So pi into 0.05 square divided by 4, we get area of the orifice as 0.001963 meter square. Also, see, to fall from, find the time required by water to fall from 1.5 meter to 1 meter. So H2 is equal to 1 meter. Also, CD is given as 0.6. So, we know for a hemispherical tank, the formula for emptying the hemispherical tank is, so case 1, H1 is 1.5 meter and H2 is equal to 1 meter. So, first case, the formula is T is equal to pi by CDA into root of 2G into 4 by 3 R H1 raised to 3 by 2 minus H2 raised to 3 by 2 minus 2 by 5 into H1 raised to 5 by 2 minus H2 raised to 5 by 2. So substitute the values, we get time T is equal to 921.4 seconds, that is equal to 15 minutes 21.4 seconds. Okay, divide it by 60. You will get 15 minutes 21.4 seconds. So second case, for completely emptying the tank. So for completely emptying the tank, you put H2 is equal to 0. So for completely emptying the tank, put H2 is equal to 0. Use the same formula. You will get T is equal to 38 minutes 6.33 seconds. You can do this of your own. You will get it to 2286.33 seconds. So divide this by 60. You will get 38 minutes 6.33 seconds. Now last problem. An orifice of diameter 10 centimeter is fitted at the bottom of a boiler drum of length 5 meter and of diameter 2 meter. So diameter of the orifice, small d is equal to 10 centimeter, that is equal to 0.1 meter, from which we get area of the orifice as pi d square by 4. So pi into 0.1 square divided by 4, we get 0.007854 meter square. Now, length of the drum is given as 5 meter and the diameter of the drum is given as 2 meter, from which we get radius of the drum is equal to 1 meter. Now, the drum is horizontal and half full of water. So, that means H1 is equal to half full of water. So, H1 is 1 meter. Find the time required to empty the boiler, which means H2 is equal to 0. CD is given as 0.6. So we know the time required to empty the tank, horizontal tank with a circular cross section. Time required to empty a horizontal tank with circular cross section is 4L by 3 into CD into A into root of 2G multiplied by 2R the whole power 3 by 2 minus 2R minus H1 the whole power 3 by 2. So we get 583.98 seconds, which is equal to 9 minutes 44 seconds. So that's all. See, you can substitute. All the values are given. L is 5 meter. CD is given as 0.6. Small a is 0.007854. G is 9.81. R is 1 meter. And H1 is 1 meter. So you can substitute, you will get 9 minutes 44 seconds. That's all. So this portion is over. So far what we have studied is, we have studied Bernoulli's equation. We have derived the Bernoulli's equation from Euler's equation. Then we saw the problems associated with that. Then we saw the applications of Bernoulli's equation, that is Venturi meter, pitot tube, orifice meter. These are the measuring devices. Then we saw the application of Bernoulli's equation for orifices. Orifices, this is a part of a tank or part of a drum or anything like that. It's a part, okay, part of the hydraulic structure. So application of Bernoulli's equation. Pitot tube is used for finding the velocity. Venturi meter and orifice meters are used for finding the discharge. So everywhere we have used Bernoulli's equation, we have used continuity equation, etc. So orifices, we had large orifice and small orifice. We had different like hemispherical orifices, circular orifice, rectangular orifice. So we saw the formula for discharges. Also we saw the formula for time required to empty the tanks. So for different cross sections, what are the formulas? And we saw problems related to this. So our next portion in the third module is flow through pipes. So that we will see in the next class. Flow through pipes, we have major and minor losses, then the hydraulic gradient line, etc. So these things we will see in the next class. Thank you for today. Thank you for listening.